Yes.
Okay. I'd like to thank the organizers, everyone who's involved in making the arrangements and everything, for the invitation to come. It's really humbling to be here and to follow such an inspirational talk as the last one. So I'm a controls engineer, robotics controls engineer, and about 14 years ago, we started focusing on the controls problem that is functional electrical stimulation. And so my presentation today is going to be a little bit different from some of the talks, although it'll parallel one of the ones previously. But focusing on closed loop control. And so I come at the problem from a little bit of a different perspective, in the sense that the students in my lab, we focus on control theory and understanding how to design functional electrical stimulation controllers in a way to achieve certain benefits and outcomes. And so I'll be talking more from an engineering perspective on how to design the stimulation inputs. This is a picture of one of my student groups from a number of years ago. There are more people in this picture that worked on stimulation. There are 3 of these individuals who are now in academics as professors teaching the same kind of closed-loop control methods. And then Matt Bellman, who you'll hear from later today, who started his own successful company. But really, this is everything I'm presenting today is really an outcome from their hard work and efforts and ingenuity. So I don't really need to motivate too much functional electrical stimulation to this audience. What I wanted to point out here is the state of the art. And when we started working on this problem, what we found is that predominantly the methods that we saw in the literature for doing functional electrical stimulation, as Stuart pointed out earlier this morning, are really what I'm going to call open loop, meaning, when Stuart talked about it, he talked about it as fixed frequency pulse trains, and a lot of the work, really pioneering work that's been done in this area has historically originated from clinicians and therapists, where they're more focused on modulating the signal. And our work is more on what is the signal to be modulated, as you'll see later on. And so when I say non-constructive control design, what I mean is that the controllers, the underlying signal that is ultimately modulated, usually isn't based on a theoretical stability analysis perspective, and that's more the approach that we take. And without doing that, sometimes that can lead to inefficient stimulation, overstimulation, because in order to achieve the desired effects, sometimes that can lead to higher stimulation frequencies and things like that will fatigue the muscle faster. So our goal is through this constructive FES design process that hopefully we will have more optimized control signals for that are applied via stimulation that will have better benefits for the muscle, such as less fatigue and things like that. The problem is that muscle stimulation is actually a really hard control problem, and the reason why is because the contractions are functions of the frequency and stimulation and intensity of the application of the stimulation. In the lower picture, you can see how the muscle geometry changes significantly throughout the range of motion. And so where you would want to stimulate can change dramatically. There's an unknown mapping between the application of force and the resultant torque output. There are variations from person to person to person. And the muscle, unlike a motor in a robot, it fatigues. So the output over time decreases. And likewise, there's a delay in the application of the input before you get a torque output. And some of our studies have shown that delay varies as the muscle fatigues. And so in order to account for all of these effects within a model and then to design a controller based on those effects is the challenge. And it's a nonlinear response as well. So this makes us think kind of two halves the coin. So one thing that this motivates us to think about are FES-specific questions, such as, how can I stimulate the muscle in a way that will prolong the number of repetitions or delay the onset of fatigue? Or how can I activate the muscle in a way that engages the user in the most active way, or forced use active therapy? And how can I design a controller that Vance mentioned earlier that adapts to the performance of the individual, so that I can just give you a product, and depending on your individual characteristics, it will auto-tune or auto-adjust itself to your specific characteristics. And those types of application questions then raise, in order to answer those questions, that raises a number of more general questions related to the theoretical design aspects. You've seen a lot today. A presentation talked about triggering when stimulation would come on, which muscle groups would come on. And so turning on and off different muscle groups and switching between the different muscle groups and switching between left leg and right leg, for example, when cycling, or upper body and lower body when cycling. You can actually destabilize and get unpredictable response when you're doing that in general. And so how can we develop controllers using certain theoretical foundations which would guarantee or provide a certificate of performance in terms of the function of the controller. And so these bullets below would be the kinds of things that we would have to think about and address from a control design perspective in order to develop these controllers. As I said earlier, there are complications or challenges to design controllers in the sense that we have dynamics that are the body segmental dynamics. This is mass times acceleration equals force kinds of dynamics. There's a desired trajectory. For example, we want to pedal a bicycle at 50 RPMs, could be a desired trajectory. And then we can measure from the actual movement of the person. We measure just the encoder on the bicycle to measure, for example, the speed. We get an error, and then we design our controller, which produces a voltage or current that's applied to the muscle. But within the muscle, then, we have these activation dynamics as well that we have to consider. So the muscle has a delayed response, as I mentioned earlier, and the delay is different between different people, and the delay changes as the muscle fatigues. There's a nonlinear recruitment curve. Stuart mentioned earlier the release of calcium, so there's a calcium dynamic that's involved there that's responsible for producing force, which is also uncertain. And then, as I mentioned earlier, there's the fatigue. The muscle will fatigue over time and at a rate that's unknown. So how to design controllers that account for these nonlinearities and these uncertainties is the challenge. So when dealing with nonlinear systems, you can't solve the nonlinear differential equations in general. And so all of the things that I'm talking about today are based on these things called Lyapunov-based theory, which in a picture, that theory just says that if you have a positive curve that decreases to zero, then you can make some conclusions about the stability and robustness of the underlying controller. And so you'll see some hints of that. I'm going to skim over the deeper mathematics on that today, but that's basically what that theory is involved in. So the first example that I want to talk about is the delay compensation. So we did a number of experiments in my lab where we varied frequency, we varied the pulse width, we varied the voltage, and across those different parameters we saw that really the delay varied from 50 milliseconds to 80 milliseconds. Within that band, in all the individuals, independent of the different parameters. And so this is a nice example of where,
Healthy individuals, right?
These are healthy individuals. And this was not fatigued. This was just the initial delay response. And this really causes a challenge in designing the controllers because these are delays in the control itself. And so that kind of makes the medicine the poison in the sense of when you're designing the controller, the delay is in the thing that you're trying to design, and how to compensate for that. So we developed these kinds of controllers. This is a proportional derivative controller, which you may be familiar with that terminology. But then, which is the E dot and the E terms at the top. But then there's this EU term, which is this integral over a time period of the control input. And this time period is the delay. And we don't know the delay. So in this controller, we had an estimate of the delay. And then that caused us to do some theoretical work here. This V is that positive function that we had to design in order to come up with this controller. But doing this kind of a controller, we were able to show an exponential kind of stability result. And so what that means is on the left-hand plot, we implemented a traditional proportional derivative controller without any compensation for the delay. And in the middle left plot, you'll see that the error swings between plus and minus, maybe even like 15 degrees of error on a leg extension test bed. And then the stimulation voltage you see is swinging pretty wildly. And for those of us who've been electrically stimulated, you know that when the voltage swings like that, it's less comfortable. And then on the right-hand plot, we kept everything the same, but we just turned on the delay compensation term that was designed and evolved from considering the nonlinear dynamics of the system. And through that process, we were able to include this delay compensation term that really had an impact. You can see that the desired is the red plot and blue is the actual. And you can see that the actual follows the desired a lot closer on the right-hand side when we added in the delay compensation. The errors are smaller, and the stimulation that we're applying is also smaller, smoother, it's more comfortable. So we can design controllers that don't include delay compensation that are stable. But this is an example of where we implemented the proportional derivative controller without the delay compensation. And here you can see it's actually destabilizing. The errors are terrible. The response by the muscle is terrible, this jerky motion. Then we, without changing anything, same person, seconds later, we didn't change the control gains. We just turned on the delay compensation term. And here you see much smoother contractions. The errors are much better behaved. So it's just a really good example of how by going into the nonlinear dynamics and from a control theory perspective, designing a controller that yielded, say, for example, this delay compensation term, that we're able to get improved performance. Because the delay also varies in time in an unknown way because of fatigue. I mean, the delay gets longer as the muscle fatigues, but the rate at which the muscle fatigues and the rate of change of the delay and what the delay ultimately is all an unknown phenomena. And so we used a neural network to estimate that change in this delay. And so this was another controller where here we had some adaptation terms within the neural network that are incorporated in the controller. that allowed it to compensate for that time varying delay. And then in implementing that controller, we got even better results because it was compensating for the time variation in the delay. So delay is related to muscle fatigue, and as many of us know, that electrical stimulation does fatigue the muscle quicker than your muscle would normally fatigue, and typically it's being applied to muscle that maybe is not as toned. And so compensating for muscle fatigue is a significant issue. When you stimulate muscle, you have to stimulate it at a high enough frequency to achieve a fused tetanus response. But the higher of a frequency that you stimulate muscle, the more rapidly you fatigue the muscle. So there's a balance there. So one of the strategies that is in the literature that we also examined is called asynchronous stimulation. And with asynchronous stimulation, the idea is, compared to conventional stimulation where you have a fixed pulse train at a certain frequency, if you were to break that pulse train up spatially across the muscle through different channels, then if I were to add each of these signals together, I would have the same overall frequency as conventional stimulation. But by breaking it apart into these different channels that are spread spatially across the muscle group, then each individual channel is at in this case, 1/4 of the duty cycle. And so by reducing the frequency by 1/4, we see that we prolong the onset of delay. And we did some experiments in individuals with spinal cord injuries, and these are the results. So on the bottom scale, you see contraction number, and on the vertical scale is normalized torque. So stimulating at 64 hertz, which is a pretty high frequency, using conventional, that's the black curve. And the red curve is the corresponding equivalent curve, but just with asynchronous stimulation. And you can see that the red curve decays much slower than the black curve. And then the blue curve is the asynchronous version of stimulation that would correspond to the green curve, where the green curve is at 32 hertz, and the corresponding, the blue curve is 8 hertz asynchronous stimulation. That's nice, but breaking the channels up across the muscle means that now I have to switch between different groups of muscle fibers. There may be some overlap, but in switching like this, now I have to take that switching into account. And so, in fact, you can think of it as switching between almost like different motors that will control the nonlinear dynamic system, because each set of muscle fibers that are affected by the channel have different characteristics. And so here we see that the voltage to torque relationship with this unknown parameter omega there, that will change for each different channel. In fact, we did some measurements to look at as we did a pulse width sweep and looked at the torque output for each of the channels. You can see that depending on which channel or where spatially across the quadricep we were stimulating, we would get a different curve. And so with this asynchronous stimulation, then, and switching across the muscle spatially in that way, we have to account for these different control effectiveness curves. Mm-hmm.
I think I had a question before, and it may be related to this too, I guess, is when you showed the first curves, you saw the black curve, you saw the red curve, and then the green curve, and the blue curve. There was a reference which was the black, and it showed that when you had the red, that you clearly fatigued slower, which was the benefit. But if I understood it right too, is you also had more force. The torque was higher.
That's right.
And so there's two effects there. One is that the asynchronous stimulation helped with the fatigue, but it also helped with the overall force.
That's correct. Yeah, I was able to produce larger force for a longer period of time. Oh, it's just because I'm able to, it's a fatigue issue in the sense that I'm able to maintain a certain level of force for a longer period of time.
So it's related to the fatigue. It's the fact that it's less fatigue, you can maintain that. Okay, I didn't see that. Because it did start off in the exact same spot.
Right.
Okay, all right.
So we have to account for the different characteristics of each channel. And in doing so, here we have some feedback components that are able to stabilize. This is a proportional derivative type of controller, and we're able to get an exponential, meaning that the error between the way it's supposed to perform and the way it performs exponentially decays to zero, which is a very strong stability result and has a lot of robustness qualities. So here's a video of the application. You can see the multiple channels across the quadricep there. And even though each channel is at a lower frequency, you still see that overall it's a nice smooth contraction. And the results from that test are that on the left is conventional stimulation, and in this middle plot you see the tracking error is increasing, and that's due to the fatigue, meaning that the controller wants to penalize the error and will stimulate the muscle with greater intensity to minimize the error. But as the muscle fatigues, you can stimulate it as intensely as you want to, but it's not going to produce enough torque. And so even as we're increasing the stimulation to the muscle, it's not able to decrease the error because of the muscle fatigue using the conventional stimulation. And in fact, even after just 30 seconds of these leg extensions, you can see that we reached an error threshold, this red line, where we terminated the experiment. And so what this meant for the individual was that the number of contractions that they were able to do in a rehabilitative session would be less than compared to the same results that we did with asynchronous stimulation. So on the asynchronous stimulation, the plots on the right, you see that the errors don't grow because we've prolonged muscle stimulation. If I carry this plot out for longer, you would see the same effect because eventually the muscle will fatigue. It's just that we've prolonged it so that now, since you don't see this error growth, we could keep doing the experiment for longer periods of time, meaning that the person can do more repetitions or get a higher dosage of the rehabilitative treatment.
But do you think that, okay, you reduced fatigue so you can experiment longer, and of course there will be fatigue at some time also in the second case, and then you will have the error. But is the error due to limitation of, so you cannot increase intensity anymore, or because of you're not matching the delay?
So there could be lots of reasons for the error, and you could design different controllers to attack the error or minimize the error. But what we were showing here is that given the same controller, that we were able to prolong it compared with a conventional stimulation versus asynchronous stimulation. Yeah.
Warren, I want to come back to just conceptually your asynchronous stimulation. The first plot showed at the various frequencies of stimulation. Now, that data shows normalized data, I believe. I imagine you normalize it either to the initial value or some other arbitrary, like a 1 rm. But does that mask the view with asynchronous, that maybe the absolute forces were different before normalization, or were they all, the absolute forces were always the same? That only works to start at 0 with the downsloping curve,
Right.
if the muscle is working as hard at 0 using the various techniques.
Sure.
Your graph doesn't actually speak to that. It speaks to a normalized effect.
Right. And we normalized by, I think it was, max voluntary contraction or max force, max voluntary force or some measure like that.
Common way, but I guess the
Right.
point is the absolute torque
Yeah.
It's all very nice to show those curves.
Right.
Is the absolute torque different between asynchronous and synchronous? Because absolute torque matters for functional activity.
Sure, and I don't have the data, and I can't remember off the top of my head. My sense is that it was basically the same because they were doing the same experiments overall, but I don't have the data to back that up. You had a question?
Could you make a brief comment on how you were selecting the electrode position and the electrodes themselves? Because basically when you would like to do a distributed simulation, you can place them anywhere on the muscle, and you obviously were selecting them for a reason.
So in order to do the comparisons as fair as possible, we took the one large pad for conventional stimulation and we drew on the person's leg an outline of that shape. And then when we put the smaller electrode pads for the different channels, we put them within that same space so that we could eliminate variations of, well, you're grabbing more surface area and maybe that's an effect that's causing it or something like that. Yeah, but you're exactly right. We could have, by having these smaller channels and distributing the stimulation across the muscle, there are different ways that you might could come up with that would be more advantageous than others on where you would put the channels.
Yeah, but you had not a particular reason why you were placing it like this, because if it's just the same area, you also can divide it like this, then you have 4 electrodes in a different position. But you just were saying like, okay, we are doing it like this.
Yeah, it was just one way to do it.
Okay.
Yeah.
Do you remember if the intensity of 4 channels on 4 channels was the same as intensity on 1 channel? So, in case of normal and asynchronous.
Yes, the intensity was exactly the same. The only thing that was different was the duty cycle per channel.
Because first time we did a study in 2009, we did a similar position, distribution of position of electrode. So we, in order to get the same torque, we need to reduce intensity to 75%. So if it was 1 channel, it was 100%, and 4 channels were each 75% to reach the same moment.
Yeah, and so since it's normalized, I don't have the data to exactly.
The reason I ask is because by doing it that way, for the smaller channel, you must have a higher current density.
That's absolutely true. Yeah.
That's going to be a big effect on the absolute torque output.
Sure. Yeah.
But still, fatigue is less, even with more.
That's right. Because
charge.
you can have a more intense contraction, but spread out over a longer period of time. Yeah. So then, kind of along this theme of switching across different electrodes, we were interested in. There's a concept of the motor point, which is the most efficient point to stimulate a muscle group. And as you can see with the bicep, that muscle group changes its position throughout the range of motion. So where is the best place to stimulate the muscle? Ideally, rather than having just one channel across the whole muscle, you would have multiple channels across the muscle. And then based on if you could build a map between where's the best place to stimulate the muscle as a function of the joint angle, then you could switch across the electrodes in order to maximize the torque throughout the whole range of motion. And that's what we're doing here. I don't know if you can quite see the different colors on the right-hand plot, but those colors represent different electrode channels that we're switching to throughout this range of motion so that we're able to follow the desired trajectory. And there's a desired trajectory curve and an actual curve, but they're on top of each other there, so you can't see the difference. And this is the map that we did. So looking at the different channels, we looked at, so for example, in the top plot, initially the blue curve, that channel produces the most torque. But then as the elbow moves, you can see that at some point the red or blue could either be used. At another point, the red is going to give you more torque output, and at some point, the green is going to give you more output. And we did experiments where we would use only one channel, or we did other experiments where we did a weighted blend of the channels based on its amount of torque contribution. So now moving on to cycling. So The same kind of mathematical structures that we use to design controllers that could switch either spatially across the limb or to reduce fatigue, or spatially across a muscle group in order to maximize torque. Now we are switching across quadriceps, hamstrings, and glutes on left leg and right leg. So there's switching among the different muscle groups and switching between left leg and right leg in order to produce FES cycling. This is one of our cycles here. This is our split crank cycle. You can see there are 2 cranks. Right now it's set up in a normal configuration, so you only see 1 chain there. But we have it set up so that you can mechanically decouple the left leg and right leg in order to do different tests. In order to combat fatigue also, we recognize that there are different places in the cycle trajectory where you're able to produce more or less torque. Meaning that when you're in this kind of a configuration in the crank, you're able to produce much more, you're able to get a lot more output for the torque that you put in, versus when you're in this configuration, you can spend a lot of torque, but you're not going to generate as much motion. And so when you're in these kind of configurations, it's not very beneficial to stimulate the muscle because you're not going to get as much result out of it as when you're in this configuration. And we did tests where we measured the torque output in these different configurations, and then we set a threshold, and we said, well, if you're above this threshold, then we will stimulate in that region, and if you're below this threshold, then it's not very efficient, and we shouldn't stimulate in that region because it'll just fatigue the muscle more rapidly. So now there are different regions throughout the crank cycle that we will want to stimulate different muscle groups because that's an efficient region to stimulate those muscle groups. And then other regions where it's not profitable to stimulate any muscle group. And from a control theory perspective, also these are the kinematics. From a control theory perspective, this causes some complications because there are periods in the crank cycle where you don't have any control authority. You're just not stimulating at all. And so an effect of that is that you could just get stuck in that region where you're not stimulating at all, and then your errors become unbounded. So we had to do a lot of work there to ensure stability and robustness with by switching through the different muscle groups. And so this is just, we broke the crank into these different regions, and then we had a strategy for switching between the different regions. Sometimes we're doing FES cycling where it's just FES, and other times we're stimulating where we have FES and a motor involved. And so sometimes we may also want to turn on a motor. And what I'll show you in a minute is it makes a lot of sense to turn on the motor in these very inefficient times for the muscle. And so when we can get an output from the muscle that is efficient, we use the muscle. And then when we're in regions where it's not really very efficient to use the muscle, then we use the motor. We could use the motor all the time, but then that doesn't get the benefit of using the muscle when you can. So you had a question?
So how did you come up with this pattern? Was it from the voluntary efforts, or when you stimulate, you see that you get these kind of movements in the particular region?
Yeah, so there are 2 answers to that. You can do it experimentally, and we did, where we had healthy normals, and we measured the torque output at the different angles throughout the crank cycle, and then we could measure the torque effectiveness at those different regions, and then say, okay, well, this is a region where it's good to stimulate, or this is a region where you're not going to get as much output. You can also actually calculate the torque at given angles as well, and in fact that matched up with our experimental measurements. So.
No, but sorry, when you're healthy, you have help of many other muscles that you can't stimulate. So I was asking, especially for the hamstrings muscle, for instance, if you stimulate, you don't know whether you're going to produce knee flexion or hip extension. And I was just asking, did you experimentally come up with these by stimulating those muscles or by getting it from the healthy pattern?
It was through experiments with healthy people. And then we've subsequently applied it to many people with different neurological conditions. So.
But she brings a very excellent point. By using able-bodied controls to set your pattern, it occurred to you, perhaps because of your own work on electromechanical delay and fatigue effects, that the optimal pattern for a person with spinal injury may be nothing like an able-bodied person's voluntary control, both for her view of muscle switching, which I think you're alluding to, but also because the muscle morphology and histochemically is also quite different than for a healthy person.
Yeah, it's a great question and something to think about, but from just a mechanics perspective, when I say you could also calculate these, there's just certain configurations where you can compute that you will generate more torque, and then you have to ask yourself, in this configuration of the crank, what muscles would then need to generate the torque there. And it's pretty clear just biomechanically that in some configurations the quadricep is the one that's going to push, or the hamstring is going to be the one that pulls. Certainly though, I think that with different...
It's tricky because it can also pull and push.
And we've seen that, yeah. And in fact, the hamstrings are very uncomfortable to stimulate, and they don't really provide a whole lot of torque anyway. And so in a lot of our experiments, we're just stimulating the quads and the glutes. Yeah. So. This is just some of the mathematics that say that when we can stimulate, we can get exponentially decaying results, but there can be instabilities when we're not stimulating the muscle. And so remember in the very beginning I said that we want a positive function that decays, but when we're not stimulating the muscle, there are periods when we have growth. And we have to monitor that very carefully, because during those periods of growth, it can actually cause unpredictable behavior or instabilities. And so because of that problem, we have these timing conditions that come out of our analysis, and the timing conditions also tell us when we should switch between different muscle groups. So we did some experiments. This is just a video of a healthy, normal person following the protocol. Unfortunately, we didn't have videos of in this experiment on people with neurological conditions. But our first protocol was able-bodied cycling, meaning that we had people without conditions. Healthy normals is a term that could be used there. And we asked them just to remain passive, don't try to cycle at all, and we stimulated their muscles to see the response. And the average error here is this red line. So you can see it's got a positive offset in the cadence tracking. The little gray box is we increase the load on the cycle during that gray box period. And you can see the controller, the errors got a little bit bigger, the stimulation got a little bit more intense, but it was able to tolerate that okay. So this is a plot of, in one crank cycle, the different muscle groups, left and right leg, that were stimulated in order to yield a cycling cadence. And I know it doesn't look very symmetric in terms of just a plot, but if you see the plot, if you compare this to the person with Parkinson's disease, I'll show you in a moment, this is a reasonably symmetric plot. I mean, even healthy normals, left leg and right leg is going to be a little bit different, and that's a little bit of differences that you see here. Then we did another protocol on someone with Parkinson's disease. The intensity of stimulation required to yield cycling for them was too much. And so in our healthy normals, they didn't get to see the desired trajectory or their actual performance. So they had no clue what was going on. They were just being stimulated and we were recording it. For this individual in protocol B, because they weren't able to tolerate that level of stimulation, we actually showed them plots of this is the desired trajectory, this is your actual trajectory, and we asked them to try to pedal at this desired speed. So they were assisting here where FES was applied on top of that. And what you notice is there's no DC offset. The cycling is about 0. And when we added the extra resistance, there's more stimulation, but the errors are a little bit higher, but okay. And here you see the very asymmetric response by this person with Parkinson's disease. The shapes on the right kind of look like the shapes that were for the healthy normal. The magnitude is smaller because they had the volitional contribution as well, but the shapes on the left are very different. And this was a result of the controller determining when to cut on for this individual in order to yield the right response. So that was kind of interesting that it could see, it produced this asymmetry in order to yield the cycling motion. So we compared volitional cadence error with cadence with FES. So in the healthy normal individuals, they were able to pedal 50 RPMs plus or minus basically 2 RPMs of error. And when we told them, okay, now do not pedal, and we're just going to apply FES, the error is like 7 RPMs of error. The person with Parkinson's disease voluntarily, they're about 5 RPMs of error, but then when we added FES on top of their ability, we were able to reduce the error by a little bit. So that was kind of nice to see. And then we also added in a motor in these developments. So in the periods, so that was just FES. And then we added in FES during certain parts of the cycle. And then in the inefficient regions, we used the motor to fill in the gaps. So different control designs. Now that this the up and off function thing that's always supposed to be decaying, now that we're using the motor in the periods that we're not using the muscle, now you're always under control, and so the errors are always decaying. And so you can see here we're stimulating the quads and hamstrings. Those are the red and blue and green curves, and then we're filling in with the black curves, which are the motor. By doing so, we got very nice response in our cadence tracking. There was a presentation earlier that noted that cycling is a repetitive process, and so we also made note of that, and we developed a repetitive learning controller. There's different ways to develop adaptive and learning controllers. We do various types of those kinds of things in my lab. But one type of adaptation that you can exploit is if the process is repetitive, there are certain adaptations that you can do that exploit the repetitive nature. And so we developed a result based on that. So this is the electrical stimulation signal that's produced by the feedback that then we modulate. And these terms with R's, those are feedback terms that accommodate for disturbances. Vance, you made the comment that, well, it's not always repetitive. There can be some differences. And these feedback terms compensate for those differences. But then we have this feed-forward component, this WD hat, which is a learning component that looks over the repetitive cycle. That's what the capital T there is, in order to minimize the error. And in a healthy normal participant, actually this is not a healthy normal participant, this is someone with a neurological condition. And I don't know why I have this video with this plot, but I think it's because on the next one I had 2 plots and there wasn't enough room. But on the healthy normal, what you can see is that over time the errors are decaying because the controller is learning and improving as it goes. And then this is for the person with a stroke. And here you see that the error, if you look at this blue curve, you can see it's going down a little bit, but not as pronounced as it was with the healthy normal, because the healthy normal is able to maintain a more repetitive cycle, whereas the person with stroke, the repetitions had a bit more disturbances in it, so it wasn't able to learn as fast. But you can still see a little bit of learning going on. And then the final, I don't know where I am on time, over I think. So the final experiment that I wanted to show you is one where, from a controls perspective, you always want, the controller's goal is to minimize the error. But from a rehabilitation perspective, if the person's able to do a certain amount, you want them to do that. Meaning that, the best rehabilitative controller is one that's not doing anything because the person's able to do it all on their own. And so we had to ask ourselves, well, how do you design a controller that minimizes an error when you want the flexibility of the person to have some error, but as long as they're doing okay, then you don't want to have the controller have an impact on them. And so we developed this idea of kind of bounding the performance. So if someone needs help, the electrical stimulation or the motor comes on, like I've shown you, to assist. And then if they exceed if they're pedaling too fast, then we increase the resistance on the bike to keep to slow their cadence. And then we have this passive mode where as long as we can keep them bounded within this region, then we just let them go. The controller cuts off and lets them do their own thing. And so this was kind of a staged experiment. The person was the healthy normal, and they could see the plots, and they were just trying to demonstrate. So during this assistive mode, so this band here, this kind of lower curve and upper curve, that's the band that we said, if you can pedal within this region, then great. The controller's not going to do anything. It's just going to let you do. But if you can't pedal at that speed, we're going to assist you to get there. And so during the first part, we told the person, hey, try not to pedal fast enough to see if the controller will come on. And so what you see is that they were receiving electrical stimulation to help them get up to speed, and they were receiving intermittent motor inputs to fill in those gaps to also help them get up to speed. And then we said, okay, now try to pedal within that speed region, and they did. And so, in fact, you can see a couple times they went a little too fast, so the motor cut in to resist them a little bit. But otherwise, everything was off. And then we said, okay, now pedal really fast. Just try and pedal and go beyond the threshold. And so you can see that we didn't allow them, the controller didn't allow them to go beyond the threshold very much because the motor would cut on and start resisting them. And what's cool about this is it's all automatic. So independent of anyone's capabilities, maybe they need all assistance or maybe they need very little, but whatever their capabilities are, they can get on the cycle and the controller will automatically adjust, including not doing anything if they can, keep it within a certain bound. So that was kind of an interesting result there. And then in conclusion, we are now working on experiments with an elliptical walker, which is essentially cycling but horizontally and using upper body and lower body. And we're also extending our early work in compensating for delays towards cycling because each muscle group has its own delay characteristic, and each muscle group comes on at different times throughout the cycle. And so the delays that the muscles are experiencing throughout the crank cycle are varying all over the place. And so I think even to your earlier comments about when to cut on and when to cut off different muscles, we found that because of the delay, that you may want to start cutting on a muscle preemptively so that when you want the muscle to be on, it will be on. And likewise, you may want to cut it off a little early so that when you really want it off, it will be off and not fighting against other muscles. And so we've characterized, we're doing studies now where we're characterizing the delay throughout the crank cycle with individual muscles, and we're kind of working towards that goal now. So that is the end of my presentation.
We have time for a few questions. In the figure before, you were showing that electrical stimulation is trying to reach this 50 RPM limit. Why is it not reaching it?
Oh.
Is the patient working actively against it?
Here?
Yeah, exactly. Because, I mean, if it's in a healthy patient, you apply stimulation and you apply more stimulation to reach your goal. Shouldn't it go up a little?
During this period here?
Yes, the assisted mode.
Yeah, so you're talking about this wiggle around 50?
No, more or less. I mean, if you ask your patient to start pedaling a little bit to get everything into motion, and then you ask him, okay, now be passive, your stimulation should try to keep it up to 50, right? Even if he is relaxing and not doing anything at all.
So, again, this was a staged experiment in a sense where during this period we asked the person to try not to pedal a little slow.
Yeah, but the stimulation should increase the speed then, right?
Yeah, and so then here what you see is the stimulation is on and the motor is on in order to get them at this green line is the bottom threshold. So 50 is the goal, but
below the green line you're not doing anything.
Yeah, but the green line is kind of the bottom threshold, where here we're assisting them to get up to at least the bottom line there, and because she's not helping at all, it just gets to the bottom line and then just kind of stays there.
Okay, I was in the beginning I was thinking like he's trying to do something, then stimulation should bring you up to the orange line, but actually it's just supposed to bring you up
to the minimum. Yeah. And then we asked them to pedal, and they were kind of able to stay in here, and then there's nothing on, and then they hit the upper threshold, and that's where it started fighting against them.
Okay, now I got it.
Okay. Stuart?
So I was real interested in that force optimization approach that you used with the multi-channel stimulation. Had you tried any other approaches? We did some work where we looked at intensity modulation as well as frequency modulation, and then combinations of those.
Okay.
And what we found is that, and this made sense physiologically to me, that if you start off with a relatively low frequency, and then first kind of get back, whenever you fall below the target, get back to your target, first modulating the intensity, and then modulating the frequency, that we had much better performance than any other approach.
Yeah.
Have you looked at any of those?
We kind of, even before the work that I presented here, we did exactly those kinds of things where, and we even did some random things where we would randomize the frequency, where we would be stimulating them at a certain frequency, and they would be doing exercise, and we would start to monitor fatigue, and we would see, okay, their performance is starting to decline. Now just change the frequency to another frequency spectrum. And in doing so, we were able to prolong. I was the first guinea pig there. This was some of Matt's work. Matt brought me in over a weekend, and I had to stop the experiment because I was able to maintain desired output, but the sensation of fatigue was so overwhelming, I just couldn't stand it. It wasn't the intensity of the stimulation. It was just, I felt just a level of fatigue that I've never felt before in my life, and I couldn't stand the sensation of fatigue anymore. So, but yet, by switching the frequencies and intensities in a similar way that I think you're describing, we were able to maintain, performance in terms of, meeting a target the entire experiment. So, Okay.
I have one question. Did you ever compare between open loop and closed loop control from cycling? Because my question is, do you believe that using closed loop control for the cadence tracking would be better in terms of maintaining pedaling without fatigue than open loop? If you apply the same pattern over, what would be starting point of that?
I have the exact same feeling that you do, but we have not tested. Is that, we haven't tested it versus open loop. Yeah. Okay, I think lunch is waiting, so I'll answer questions all day.